Let's take a look at exam 3 practice test. So this is the video for the test review. Now just a quick note, I can't find my microphone, so hopefully the sound quality on this video is okay. If you have any questions about anything I said, just let me know. I'll try and answer those questions for you. All right, the first question says to find the domain of the functions. So if I have a rational function, to find the domain, we are going to find the restrictions. So we know that x minus 5 cannot equal 0 because our denominator can't be 0. So that means that x cannot equal 5. So there's essentially our domain. If you write it in the correct notation, the domain would be that x can be all real numbers except for x cannot equal 5. That's a great way to write the domain when you want to show that it can be everything with one exception, one or two exceptions. All right, the next question then is very similar. We have that the denominator is x squared minus 1. So the denominator cannot equal 0. So x squared minus 1 is not equal to 0. We factor that, and we get that x cannot equal negative 1 or 1. So if we write the domain out, we have here that x can be all real numbers except for x cannot equal negative 1 or 1. And then the last one, this one's a little different because we have a square root. The inside of our square root must be greater than or equal to 0. So if we go and we solve this inequality, we have that 4x must be greater than or equal to 26. Divide by 4, we have x is greater than or equal to 26 fourths or 13 halves. Now, we don't want to write it in set builder notation. We want our final answer in interval notation. So if you want to find the interval notation here, we have 13 halves, and its x is greater than 13 halves. So our interval notation for our domain is that we will go from 13 halves to infinity. Okay, so that is finding the domain. The next question just tells us to perform the operations. So if we're going to perform the operations, let's take a look. The first one is a multiplication. So what we want to do with multiplication and division is that we need to factor everything all the way out. So here I'm going to factor the numerator. So the factors of negative 10 are x plus 5, x minus 2. The factors of x to the fourth minus 4 are x plus 2, x minus 2, times, let's see, on this one we need to factor out a 2. Then we end up with 2 x squared plus x minus 6. Take the 2, multiply the 6. That gives me x squared plus x minus 12, which would be x plus 4, x minus 3. We need to go and divide by 2, reduce x plus 2, 2x minus 3. So, go and do that. We have 2 times x plus 2, 2x minus 3. And in the denominator, that one's a little bit easier. We have 2x plus 3, 2x minus 3. All right. Now let's cancel out any common factors. That's the fun part, right? We have this x plus 2 there. And our final answer is everything in the numerator, which is 2 times x plus 5, over whatever's left in the denominator. You can distribute that 2 through if you want, but there's no need. So that is our final answer with the multiplication. Now let's take a look at a division one. That would be B. All right, so same idea. We're going to go ahead and factor everything that can be factored. So we have here x plus 6, x minus 1. Then here it's x minus 6, x plus 5. All right, and then factoring these ones, there's no common factor. So I'm going to take that 3, multiply the last term, factor, and then divide by 3. So my factors would be x minus 1, 3x minus 2, and my bottom one, let's see, that's x squared minus 17x plus 30. I did not give myself enough room. We have x minus 15, x minus 2, divide both by 3, and our factors are x minus 5, 3x minus 2. Great. Okay, now we just go ahead. We're going to flip the back fraction. If you're very comfortable, you can go ahead and flip the fraction as you're factoring. So when we flip the back fraction, anything that was in the denominator comes up, anything in the numerator goes down. Okay, and then we get to cancel any common factors. So here, the x minus 1s, the 3x minus 2s, and that looks like that is it. So we have x plus 6, x minus 5, x minus 6, x plus 5. And those are unique factors from each other, so we can't do any more canceling. Let's go ahead now and add and subtract fractions, which is a little bit harder than just doing the multiplication and division. So let's look here at C. So what we want to do, there's still some factoring involved. So what I want to do is I want to factor the denominators. We do not need to factor any numerators. So that's where I'm going to start. I'm going to factor. So let's see the factors. It's x minus 4, x minus 1. Okay, so once we factor, we need to find the LCD. The LCD is just all the factors that my denominators have. So my first fraction, I have the factors of x plus 1, x minus 1. So those are factors included in the LCD. And then on my second fraction, I have an x minus 4. And then I have an x minus 1. But x minus 1 is already included as part of my LCD, so I don't need to write it twice. Okay. The only time you would ever have to write a factor twice as part of the LCD is if that factor was like squared in the denominator, or you had two of the same factors in one denominator. Okay, so what we're going to do is we are going to go ahead and solve these equations, or balance out the denominators So let's start with this first one. We have x plus 1, x minus 1. It is missing an x minus 4. So I'm going to multiply the numerator and the denominator of my fraction by the part of the LCD that fraction is missing. Okay? And then in my other fraction, I am missing an x plus 1. So I'm going to multiply the top and bottom by x plus 1. Now, once I do that, notice that my denominators are completely the same. So I have x minus 4, x plus 1, x minus 1. They don't have to be written in the same order as long as they have the exact same factors on both. Now, we just distribute it through the numerators. We have 3x minus 12 plus 8x plus 8 all over my LCD, which is x minus 4, x plus 1, x minus 1. Okay, combine like terms. We have 11x minus 4. Let's see here. All over x minus 4 times x plus 1 times x minus 1. All right, so that's our final answer. You do not need to FOIL through anything. There we go. All right, let's look at D. So D is going to be the same process. Just a little bit more factoring. Let's see here. I have 5x over x plus 3, x minus 2, minus x minus 2. Now I'm going to put parentheses around those because I think that will help me in the long run. We have here x plus 3, x minus 1, plus 8x over x, not plus 2, x minus 2, x minus 1. Okay, so we're going to go ahead and find the LCD again. So my first term, I have an x plus 3 and an x minus 2. On my second one, I have an x plus 3, which is already included, and an x minus 1. So I'm going to include that x minus 1. And then my last one, I have an x minus 2, x minus 1. So both are already included. So we're going to go through and balance out each of our fractions with what it's missing. So I have x plus 3, x minus 2 on my first fraction. So I need an x minus 1. Okay. On my second fraction, I have an x plus 3 and an x minus 1. I need an x minus 2. And then on my last fraction, I have x plus 3, or x minus 2, x minus 1, and I need an x plus 3. All right. So now all of my denominators are the same, which means I can then rewrite my numerator all as 1. And this is not going to be pretty foiling this all out, but we can do it. All right, so I'm going to distribute this 5x through. That gives me 5x squared minus 5x, then minus, I'm going to FOIL this. This is x squared minus 4x plus 4. Notice that I kept that in parentheses because I'm subtracting it all. Okay, and then plus, let's distribute that 8x. That's 8x squared plus 24x. All over my LCD, which is, what if I just write LCD here? I'll put that in at the end. Okay, So 5x squared minus 5x. I'm going to distribute that minus sign through. There's nothing like doing a whole problem or doing a whole extra step just to distribute a minus sign through. If you're real good, you can distribute it through whenever, but there we go. Okay. Now, I'm going to just combine like terms. I have 5x squared minus x squared is 4x squared plus 8x is 12x squared. I have 5x plus 4x is negative 1x plus 24 is 23x and then minus 4. All of that over my LCD. Okay, this is a pretty long problem. If we had one like this, it would definitely be in the written section. All right. Okay, so there you go. That is adding and subtracting irrational equations at the same time. All right, the good news is that is it for the first page. And personally, I think that adding and subtracting rational expressions is one of the harder things in this unit. So if you can get through that, you are on your way to doing great things. Okay, so page 2, we have these complex rational fractions. They're pretty tricky, so let's take a look. All right, so with the complex rational expressions, the very first thing you want to do is let's go through and factor any of our denominators. Now, I don't think this one's going to turn out very clean, but let's see. All right. So what I'm going to do here is I'm going to find the LCD between my denominators. So here's each of my denominators. I am going to find the LCD between them. Okay, so what I want to do, I have here a 3. I have an a plus 5, an a minus 1, and an a plus 1. So that is my LCD between all of the denominators. What I am going to do is I'm going to go and multiply every single one of my denominators by that LCD. So I have 3, a plus 5, a minus 1, a plus 1 times 10. So in that case, the 3 and the a plus 5 are going to cancel. Then I'm going to go minus 5 times 3 times a plus 5 times a minus 1 times a plus 1. In that case, the a minus 1s are going to cancel out. Then on the bottom, I have here 3 times a plus 5, a minus 1, a plus 1. Ooh, there's lots of things that will cancel out on that one. Okay, so what we are left with here, we have a 10 times a minus 1, a plus 1, minus 5 times a 3, that's 15, a plus 5 times a minus or plus 1, all over a plus 5. At least that denominator canceled out cleanly. Okay, so what we are going to do is distribute. Oh, that's fun. That's a squared minus 1 minus 15 a squared plus 1a plus 5a is plus 6a plus 5 all over a plus 5. Okay, we still need some more distributing. So we have 10a squared minus 10. Then I'm going to go negative 15 times each term. So negative 15 times a squared is negative 15a squared. Negative 15 times 6a is negative 90a. And negative 15 times 5 is negative 75. And if you combine like terms, we end up with negative 5a squared minus 90a minus 85 all over a plus 5. All right, so that was pretty intense. Okay, the next one, B, is kind of similar. Let's take a look. Same thing, we need to factor those denominators. So I end up with here 12 over 3b plus 9 over, let's factor out the b minus 8 all over 4 times b minus 2. Okay, there is one thing that I want to do before I actually find the LCD, and it's right here. That 12 over 3 can be reduced so that I have instead 4 over b plus 9b, b minus 8, all over 4b minus 2. It might help, it might not. At the end, we would have had a reducing if we didn't do that. So it's just a little bit of an easier process for us. Okay, so now we go ahead and find the LCD. I have b, and then on the second one I have b times b minus 8, so I need a b minus 8, and then I have a b minus 2. Okay, so go ahead. We're going to multiply everything by b minus 8, b minus 2. Every single little fraction gets that denominator. Okay, so then we're going to cancel the b's out on the first one, both of those on the second, and the b minus 2's in the bottom. So we are left with 4 times b minus 8 times b minus 2 plus 9 times b minus 2 all over 4b, b minus 8. Okay, so I'm just going to do some distributing here. 4b squared minus 10b plus 16 plus 9b minus 18. I'm going to do that real quick. 4b squared minus 40b plus 64 plus 9b minus 18 all over our denominator. And we get here 4b squared, and then we've got 40b plus 9b is minus 31b. And then 64 minus 18 is 46. All over 4b times b minus 8. And there we go. Those are our complex fractions. You just simplify them. You know a complex fraction is simplified when there are no fractions within fractions, and everything that can be reduced is reduced. All right, the next problem that we're going to take a look at is the long division. This is definitely the longest problem on here. So what we want to do is we want to start by setting the problem up. We're going to take this 2x plus 4 and we're going to divide it into, we have 2x cubed plus 8x squared. Notice that I have no x's, so I'm going to write 0x minus 12. You must have a placeholder there. All right, now let's go do the process. We have, how many times does 2x go into 2x cubed? That would be x squared. Then we're going to multiply. So first we divide, then we multiply. So x squared times 2x squared is 2x cubed, and x squared times 4 is 4x squared. Then we change each thing's sign, so anything that's a negative becomes positive, anything that's positive becomes negative. Okay, 8x squared minus 4x squared is 4x squared plus 0x minus 12. Okay, now we're going to just repeat the process. We're going to do the division. How many times does 2x go into 4x squared? That would be 2x times. Then we're going to go 2x times 2x is 4x squared. 2x times 4 is 8x. We're going to subtract each thing. We get 0, negative 8x minus 12. Then how many times does 2x go into negative 8x? That's negative 4. Multiply. Change each thing's sign. We get negative 12 plus 16 is 4. So our final answer then, or 2x cannot go into 4, so we have x squared plus 2x minus 4 plus 4 over the divisor. And that is our final answer. Okay, so that is it for page 2. Let's go ahead and go on to the next page. Okay, so questions 5A through J is this next page. This might be the hardest page. Let's take a look. So in this first one, we have the square root of 36 plus 81. Here we must add those first. 36 plus 81 is, 117. Okay, now we want to check to see if we can factor that. All right, so I had to use a calculator to check this, but 117 is 9 times 13. Which means that we can simplify that by taking the square root of 9 is 3 and then 13. So we must add inside the parentheses before we add out, or before we take the square root. All right, the next question is the same idea. So I have 100 plus 28 is 128. The factors of 128 are 64 times 2, and the square root of 64 is 8. I cannot take the square root of 2, so that is our final answer. Okay, C. So let's see, we have 32 over 16. I'm going to reduce that first. 32 divided by 16 is actually 2. So I have 2 to the 3 halves power. So what I have then, I have 2, the square root of 2 to the third. Well, I'm going to do something. I'm going to make that, I'm going to go 2 cubed is 8, and then the square root of 8 is 2 square roots of 2. So there we go. Kind of a little tricky one. It wasn't exactly what I wanted with the problem, but it's good to see that you can reduce with the fraction before you take the exponent. All right, so on D, I have here, I want to take the fifth root first of 243 over 1024. And then after we do that, we'll take those to the third power. Okay, the fifth root of 243 is 3. And the fifth root of 1024 is 4. You would probably want to use a calculator on those ones. Then, once I do that, I'm going to just cube each one. 3 cubed is 27, and 4 cubed is 64. There is our final answer. Okay, so for E, we actually want to multiply the constants and then the insides. If I have 2 times 3, that is 6. And then 18 times 5 is 90. We can rewrite 90 as the factors of 9 times 10. The square root of 9 is 3, so I'm going to multiply it out in front. And then 6 times 3 is 18. And I can't do anything with the square root of 10, so that is our answer. All right, let's take a look at F. So we have here 9 square root of 46 times 4 times the square root of 12. Okay, so I want to go 9 times 4 first, that's 36. Then we're going to go 46 times 12. Okay, which is 552. Then I'm going to just check 552 for factors. The only factor I found, and if this were like a multiple choice question, I definitely wouldn't have the numbers quite so big, but that's okay. You have 4 times 138. Let's bring the 4 out. And then 36 times 2 is 72 square root 138. And that's our final answer. Okay, G, I have 2 square root of 72 plus 10 square root of 8. So I need to simplify the square root of 72 and the square root of 8. So 72 is 36 times 2. The square root is 6. 36 is 6. 2 times 6 is 12. 10 is 4 times 2. The square root of 4 is 2. 2 times 10 is 20. Square root of 2. 12 plus 20 is 32. Square roots of 2. Now it's really nice when you add them and then they have, or when you simplify them and then you can add them because they have the common factors. H I don't think is going to be that clean. So here we have 2. I'm going to rewrite 99 as 9 times 11. And 121 is a perfect square root. So the square root of 9 is 3. 2 times 3 is 6. And then here, the square root of 121 is 11. There we go. Okay, there is nothing we can do with this. We can't combine the 6 square roots of 11 with the 33. So that's our final answer. Okay, this one's tricky. I and J, but follow along very closely because they are very important. So I have here, I'm going to multiply through using the product rule because I have the same index number. Okay, the 3's. All right, now what we're going to do, we have 25 times 5 is the cube root of 125. Then I have x times x squared, or x cubed times x squared is x to the 5th. I have y to the 5th times y is y to the 6th. And I have z to the 4th times z to the 3rd is z to the 7th. Okay. From here, now we're going to look for perfect cubes. In fact, this is a perfect cube and my y is a perfect cube. But I can rewrite my entire problem so that every term has a product of a perfect cube. So x to the 5th is not a perfect cube, but x to the 3rd is. So if I break x to the 5th up as x cubed times x squared, then I have the product of a perfect cube times whatever's left over. Same thing with z to the 7th. I have z to the 6th times z to the 1st. All right, then what I can do is I have my perfect cubes there, and I just pull them out. The cube root of 125 is 5. The cube root of x cubed is x. The cube root of y to the 6th is y squared. And the cube root of z to the 6th is z squared. Then, anything that is not a perfect cube stays inside. All right, so there you go. Okay, J is kind of similar because the product rule and the quotient rule are kind of the same rule. So what we can do is we're going to rewrite each of those under one radical, x to the 4th, y to the 6th. Okay, and I'm going to reduce the fraction. 540 divided by 20 is 27. X to the 4th over x to the 4th cancels, and y cubed over y to the 6th is y cubed in the denominator. All right, now both of those are perfect cubes, so the cube root of 27 is 3, and the cube root of y cubed is y. And there we go, that is our final answer. And that is it for the first page, or the third page. Let's go ahead and move on to the last page. Okay, let's take a good look at question 6. We need to rationalize the denominator. That is particularly hard for this our first question. We want to multiply the top and the bottom by the 4th root of something so that I have a perfect 4th power in my denominator. So right here, this 36 is 6 squared. I have x, y to the 8th. I want each one of these to be a perfect 4th power. So if I have 6 squared, I need 2 more 6's to get that to be 6 to the 4th. If I have x to the 1st, I need 3 more x's to get that to be a perfect 4th power. And I have here y to the 8th. Y to the 8th already is a perfect 4th power, so we are good. All right, I'm going to rewrite this then. I have 12x to the 4th y times the 4th root of 36x cubed all over the 4th root of 6 to the 4th power x to the 4th, y to the 8th. Okay. Now what I'm going to do is I'm going to simplify that radical. It's a perfect 4th. So I have here 12 x to the 4th y, 4th root of 36x cubed, all over 6xy squared. Okay, now these can all be reduced. So I have 12 over 6 is 2. X to the 4th over x cubed is x cubed. Y over y squared is y. And then we just have the 4th root of 36x cubed. And that is our final answer. All right, definitely a harder type of problem that you would do. Let's take a look at B though. I don't think B is quite as tricky. With B, we simply need to multiply the top and the bottom by the denominator's conjugate. Whenever we have a radical, whether the radical is like what we see here, or if the radical is in the form of an imaginary number with an I, we need to multiply the top and bottom through by the conjugate. So I'm going to distribute here. That gives me 45 plus 9 square root of 2. On the bottom I have 5 times 5 is 25, plus 5 square root of 2, minus 5 square root of 2, minus 2, which ends up being 45 plus 9 square root of 2 over 23. Now, if you really want to break that up, you can. In this case, it doesn't matter as much as it does with the imaginary numbers. So I'm not really too concerned about that. But there you go if you want to see it either way. That is rationalizing our denominator. Okay, these last problems here, we're going to divide the complex number. Well, I didn't get too creative with these denominators, but whenever you're dividing a complex number, you just need to multiply the top and bottom by the conjugate. So I have here 15 plus 5i divided by, let's see, I'll FOIL this all the way out. 9 plus 3i minus 3i minus I squared. Okay, so that means we have 15 plus 5i divided by 9 minus negative 1. Okay, so 15 plus 5i all over 10. We do want to take that 10 and divide it into each term because we need to write this as a complex number. So 15 over 10, let's see, 5 goes into both, so that's 3 halves. 5 also goes into both here. We get 3 halves plus 1 half I. Or if you wrote that 3 halves plus I over 2, that is also correct. It doesn't matter either way. Okay, our last one here. I really did not get creative with these denominators. I have 3 plus I, 3 plus I again. So I have my first, which is 6. Outer, that's 2i. Inner, that's 3i. And last is plus I squared. All over, we already know that 3 minus I times 3 plus I is 10, so I just kind of took the shortcut there. We end up with 6 plus 5i minus 1 over 10, or 5 plus 5i over 10, which is 5 over 10 plus 5i over 10, and reduced, that is just 1 half plus 1 half I. All right, that is it for Exam 3 test review. Good luck.